Okay, today we're talking about the common ion effect as it affects acid-base equilibrium, and this will lead into development of the Henderson-Hasselbalch equation. So we know from Le Chatelier's principle that the extent of ionization of a weak electrolyte is decreased by the adding to the solution a strong electrolyte that has an anion in common with the weak electrolyte. To give you an example, we show a calculation where nitrous acid, which dissociates into the nitrite anion and the proton, is mixed with potassium nitrite. So now the common ion is the nitrite anion. There's nitrite coming from the nitrous acid, and there's nitrite coming from the potassium nitrite. That's going to have an effect on the equilibrium. Le Chatelier's principle tells us that if you disturb an equilibrium by adding an excess of something, the equilibrium will shift so that the excess substance is absorbed or diminished, so that we reestablish the equilibrium or come closer to reestablishing the equilibrium concentration. In this case, we are told that a 0.085 molar solution of nitrous acid has 0.1 molar potassium nitrite added to it. So what is the effect going to be on the pH? Well, we start off with a 0.085. It's good to have an ice table in situations like this because it helps us sort out what all the concentrations are. We're going to assume an amount X of the nitrous acid dissociates, so at equilibrium we're going to have 0.085 minus X. Because of the presence of potassium nitrite, the nitrite concentration is going to start off at 0.1. It's not going to be 0, it's going to be 0.1. And an extra amount X is going to appear when the nitrous acid dissociates. So that at equilibrium we're going to have 0.1 plus X. And the proton concentration will be 0 at the outset, and an amount X will appear as the nitrous acid dissociates, so that at equilibrium we have X. We set up the equation so that the Ka value equals products over reactants. We enter all our quantities, and we're going to use the quadratic formula to solve this one. Iteration would not be a good idea in this occasion. And we get two values, x1 and x2. One of them is negative, so we discard it. And we're left with the correct answer, which is the concentration of protons at equilibrium. Take the negative log of the H plus concentration, we get a pH of 3.42. In this example, which is from page 724, it's a practice exercise from our textbook, we're asked to find the formate ion concentration in a solution that is mixed with 0.1 molar nitric acid. So we have a strong acid being mixed with a weak acid. And we know from previous examples that mixing a strong acid with a weak acid will suppress the ionization of the weak acid. So here is the formic acid, to give you, which dissociates to give you the formate anion and the proton. The initial concentration is 0.05, and we've added 0.1 molar H plus in the form of nitric acid. Remember, nitric acid is a strong acid which dissociates 100%. So whatever concentration of nitric acid is added, we'll get the same amount of concentration of protons. An additional amount of protons forms as a result of the ionization of the formic acid. So we're going to call that amount X. Whatever amount of formic acid dissociates will decrease the concentration of formic acid by X, which means it will increase the concentration of formate anion and the concentration of protons. So at equilibrium, we're going to have 0.1 plus X protons, X formate, and 0.05 minus X formic acid. Again, we enter all the values into the value for the expression for Ka, which is products over reactants. We substitute all the numbers that we've discerned from the ice table. We use the quadratic formula. And what we conclude from the calculation is that very little formate ion forms because of the suppression of ionization from the nitric acid. And we get 9.0 times 10 to the minus 5 molar concentration of formate anion. Whenever you have situations where a weak acid is partially neutralized, there's going to be the formation of the conjugate base and the acid. This gives rise to what is called buffering. And a buffered solution is a solution which contains both a weak acid and its conjugate base. And these solutions are capable of resisting changes in pH because whether you add acid or base, either the acid or the conjugate base reacts with whatever is added. So those solutions will resist pH changes. If hydrogen ion is added to a buffer, it reacts with the conjugate base in solution. And if hydroxide is added to a buffer, it reacts with the acid that is in solution. The Henderson-Hasselbalch equation is derived.
Mr. Miller's Period 3 class, please report to the main office. Mr. Miller's Period 3 class, please report to the main office.
The Henderson-Hasselbalch equation was derived to help us calculate the pH more easily. And it starts off with Ka. We isolate for hydrogen ion concentration, then take the negative log of both sides. And what gives us negative log of H plus is equal to negative log of Ka minus the log of HA over A, where HA is the unassociated acid and A minus is the conjugate base. The negative log of H plus is pH, and the negative log of Ka is the pKa. And then if we flip the terms on the log, we can change the sign. So we get what's called the Henderson-Hasselbalch equation here, where each acid has its own pKa value, and the concentration of the conjugate acid and the conjugate base and the acid will tell us what the pH is. Just want you to note that when the pH equals the pKa, the proportion of acid and its conjugate base are equal. It's 50% ionized if the pH is equal to the pKa.